Hello, welcome to the British Geological Survey. My name is William Lyons and today I will be talking about the acquisition and operation of the TOC-L instrument. After experiencing technical issues with the current instrumentation used to analyse samples for non-purgeable organic carbon, a new TOC-L CPH instrument was bought for Christmas. TOC stands for Total Organic Carbon. To acquire a new instrument, sufficient funds need to be available, and evidence needed to be provided as to why that particular company was chosen. The evidence was in the form of quotes, with a minimum of 3 required. I got in contact with a few companies, for example Elementar, GE Analytical and Shimadzu. For these I had to ensure the basic instrumentation was present with an autosampler. Also I had to ensure any chemicals required, installation costs and delivery charges were included. From this the team judged the best choice based on their functions. For example, each instrument has different limits of detection, time taken, sample volume, and types of samples that can be analysed. However, we also considered the reliability of the current instrumentation, which is a TOC-V by Shimadzu. Following this, we purchased a Shimadzu TOC-L, an upgrade of the current instrumentation. This judgment is justified by an overall understanding of the TOC instruments by Shimadzu, for example, having the knowledge to replace parts and solve problems that may occur 10 years in the future. Why do we need a TOC-L? The main reason people need to measure carbon is for process control and regulatory checks. Some good examples include municipal drinking water, as organic carbon reacts with disinfection chemicals such as chlorine. This forms disinfection byproducts, which may be carcinogenic. Another is in pharmaceutical manufacturing, where water is the most commonly used ingredient to produce drugs. Regulations limit the concentration of organic carbon to prevent harmful bacteria from growing. Additionally, TOC analysis is used in electronics manufacturing, where ultra-pure water is needed to manufacture microprocessors and computer chips to prevent microscopic damage to these miniature circuits. What can the TOC-L do? The TOC-L and TOC-V are capable of TC, IC, MPOC and POC. So what does this all mean? TC. There are 2 types of carbon in water samples, organic and inorganic. Organic carbon forms organic compounds using hydrogen and oxygen, whereas inorganic carbon is the basis of carbonates. TC, total carbon, is the sum of the organic and inorganic carbon within a water sample. The instrument uses the organic and inorganic carbon to produce carbon dioxide and determine a result. IC stands for inorganic carbon and measures only the inorganic carbon. This is done by acidifying carbonates such as methyl carbonate, using hydrochloric acid to pH 3 or lower to produce carbon dioxide. The sample is sparged to remove the CO2 so it can be measured. Sparging is where a chemically inert gas is bubbled through a liquid. MPOC stands for non-purgeable organic carbon. The instrument acidifies the sample and removes the inorganic carbon using sparging via the IC method. The remaining carbon, which is organic, is oxidized to CO2 and the resulting CO2 measured. POC, purgeable organic carbon. The instrument acidifies the inorganic carbon and removes it using sparging. However, when sparging, purgeable organic carbon is also removed. So, the sparge gas is carried to a lithium hydroxide filled CO2 absorber to eliminate the CO2 produced by the inorganic carbon. This leaves the purgeable organic carbon, also known as volatile organic carbon. So what are the similarities and differences? Overall, the TOC-L and TOC-V are very similar instruments, but there are 2 new improvements: the measurement range and the temperature. This allows a wider variety of samples to be potentially analysed, i.e. peat samples very high in carbon, and a higher temperature option to allow for more accurate organic carbon oxidation, ensuring all the carbon is oxidised. First we take a 9mm vial and fill it to about 6 to 8 mL for the sample. Then we place foil on top of the vial. This is to prevent light degradation and from CO2 escaping from the sample. Then we place this sample into the rack. And we take the rack and place it into the autosampler of the TOC-L. A needle comes down, pierces the foil and draws up the liquid through the PTFE tubing using the syringe. At this point, any dilutions required occur. Then 1 molar hydrochloric acid is added to the sample inside the syringe to remove any inorganic carbon. All these additions are done by using the 8-port valve, having 8 tubes surrounded by a central tube the syringe inserts into. The key ones being the sample, offline, diluent, acid, combustion tube and IC port. The next stage for the sample is to be sparged using a carrier gas, removing any inorganic carbon. Here is a brief video by Shimadzu entailing this process. The carrier gas is pressurized air that flows out of a compressed air supply and into the gas generator. The gas generator employs catalytic oxidation to remove hydrocarbons to 0.05 ppm, carbon dioxide to 1 ppm, and water vapour to 1 ppm, and carbon monoxide to 1 ppm. This reduces potential carbon dioxide introduction into the instrument and avoids having to purchase high pressure cylinders of air, nitrogen or oxygen. Our gas supply is too pressurised for the TOC-L, so on installation a pressure regulator was fitted. This to prevent tubing becoming loose or damage occurring to the detector. So the gas flows from the gas generator out and through the blue tubing into the instrument, all the way through and into the gas regulator. The carrier gas then flows via 2 routes, the first being through the syringe. So it goes into the regulator, out, round, and through this tube here, which comes through the front, down, and into the syringe, where it's used to sparge the sample, and then this sample is then injected into the combustion tube, which is at the top here. The second is a continuous process whereby the carrier gas flows through the humidifier and into the combustion tube. It is humidified to allow both dry and wet chemical oxidation to occur within the combustion tube. This allows a greater efficiency of conversion of organic carbon to CO2. The combustion tube is a quartz tube surrounded by a ceramic tube and glass wool. So there is the ceramic tube and there is the glass wool. Here we have a motor and we have a fan. When the sample enters the combustion tube, a motor pulls the tube across the top and the syringe injects the sample into the combustion tube. If the motor melted, the tube would not be fully pulled over, and if the plastic block melted, there'd be a gap, so air from the environment would be able to enter, allowing CO2 from the air to cause increased interference. The organic carbon is oxidized at 680 degrees in the combustion tube, using a platinum catalyst supported by alumina pellets, which is this. The platinum works as a catalyst by loosely binding to oxygen atoms, making them readily available to oxidize the organic carbon. Once this is complete, the resulting vapour runs through a cooling tube, so from the combustion tube into the cooling tube. In the TOC-L, this is a glass cooling tube. However, in the TOC-V, this is a PTFE tube. The sample is forced through using the carrier gas and goes into the pure water trap. So through this tube, into the pure water trap. The gas comes in with the water collects inside, and the gas flows onward into the dehumidifier unit to remove any residual water. All the wastewater is collected in the drain pot, then the sample and carrier gas flow into the dehumidifier unit. Next, the gas flows through the halogen scrubber. The halogen scrubber is a bundle of copper wire and reacts with halogens, so chlorine and bromine, that could have been present in the water sample. Copper fluoride is white, copper chloride is yellow-brown, and copper bromide is black. Should the halogen scrubber go black, this means there's a build-up of copper bromide. The carrier gas and CO2 then flow through a membrane filter of 0.45 to remove any particulates. These may form residues in the detector or tubing. This either goes into the detector or into the CO2 absorber. The CO2 scrubber is used to remove CO2 from the carrier gas when no sample is present. The carrier gas can flow through the scrubber, CO2 absorbed, then purge the optical system of the detector, i.e. the gold tube. This consists of potassium hydroxide, sodium hydroxide, and calcium hydroxide. These react with carbon dioxide to form carbonates and water. Why is it crucial to remove water, particulates, and halogens? The detector is a non-dispersive IR detector. Inside it's lined with gold. The gold is used to reflect the infrared light. The halogens would react and remove it, the particulates would decrease the IR reflections by depositing on the gold, and water is polar, therefore absorbing IR. Overall, the sample goes into the combustion tube, into the cooling tube, through the water trap, through the dehumidifier, the halogen scrubber and the membrane filter, and then into the detector. I hope you've all enjoyed hearing about the new TOC-L, and thank you all for listening.